Hi, and welcome back. In this lesson, we will use the makefile to build our Smith-Waterman targeting the VU9P FPGA on Amazon F1. Let's open the terminal and continue from where we left last time. The first thing to do is to clone the AWS FPGA repository, as it contains all the necessary drivers to use the SDXL on the AWS environment. Once the repository has been cloned, we have to navigate inside and source the SDXL setup SH file. Awesome! The script setted our environment and downloaded all the necessary drivers for using SDXL on this platform. Now, the version of SDXL on the AWS instance comes with no hardware specification of the target FPGA. However, we can find this specification if we navigate to SDXL and then AWS platform. Now, in order to be able to synthesize for the specific FPGA, we can either refer to this location when setting the target architecture in the Xilinx compiler, XOCC, or we can copy the folder containing the driver of the specific board into the platform folder that is located in SDXL installation location. For this example, we will perform this second operation. Let's copy then the board we want to target, that is the one with 4 physical ports with the DDR4 and the SA version 4.0. Great! I have pre-created a Smith-Waterman folder on this instance containing the latest version of the code we have synthesized for the Kintex Ultrascale. However, in order to use it on this new target architecture, we need to specify the new FPGA in the makefile. Hence, let's change the target device variable to AWS-VU9P-F1 with 4DDR-XPR2PR and DSA version 4.0. Awesome! Now, in order to build the binaries, we just need to type make build target equal to hardware. Fantastic! The binaries have been generated. Now, in order to execute them on the FPGA, AWS required to first register the generated binaries and then move to an F1 instance. That is the instance that is actually equipped with the VU9P FPGA. So, if we come back to the AWS FPGA repo, under the SDXL folder, there is a README describing the process we are going to perform. But before creating the Amazon FPGA image, we need to set up the command line interface and create the S3 bucket. In order to perform this first operation, it is necessary to know the access key ID and secret access key of the user registering the image. All this information are available in the Identity and Access Management Service, or AMI. To start configuring the command line interface, we have to type AWS configure, specify the access key ID and secret access key, the region that, as we can see from the GitHub repo, have been set to, as an example, US East 1, and then the output format, that is JSON. Easy, right? Now, we just have to create the bucket and then 2 folders, the DCP for the tarball files and the logs one, to keep track of logs. Let's start with the second operation, and let's call the bucket SW2DDR, specifying the US East 1 region. Now, in order to create the 2 folders mentioned before, we just have to add slash plus the name of the folder to the previous command. As usual, my great fantasy brings me to call the first folder DCP and the second one logs. The cp command here is just an example of how it is possible to copy the filesgohere.txt file into our DCP folder, into the SW2DDR bucket. Now that we have the bucket, we can use the script provided into the AWS FPGA repository to register our AFI. As our environment has been already set it up, we can directly type the path to the script using the SDXL dir environmental variable, then specify the name of our XCL bin file, the output name of the AWS XCL bin file we want to generate, the name of the bucket, and the name of the logs and DCP folders. Okay, there is an error. Let's fix it really fast and then launch the command again. Great, it worked! Look how many files have been generated now. There is even the AWS XL bin. Although the file has been already generated here, it will be available only when the registration of our AFI will be approved. To check the status of the registration of the image, we need first to check what is written in the AFI ID.txt file, where it is provided an FPGA image ID. With this value, we can use the Describe FPGA Images API provided by AWS to see the state of the image. As of now, it is still pending. Hence, we need to wait a little bit before executing on the FPGA. Notice that once the image will be approved, the only things we need to execute on the FPGA device are the host file and the AWS XL bin. We do not need anymore the XL bin generated with SDXL. Let's try now to call the Describe FPGA Images to see if the image has been now accepted. Awesome! It is available. It means that now we can run these binaries on the FPGA device. For this example, I will directly copy my host and AWS XL bin binaries on a new F1 instance. Let's start by requesting an F1 instance. For this example, we will request an F1 instance equipped with a single FPGA board. Now, let's connect to the instance, and let's clone the AWS FPGA repo on this new instance. After sourcing the SDXL setup script, we have now a configured environment on this instance too. Now, the only thing we have left is to execute the binaries that we have created. In the AWS FPGA repository, the README clearly explains how to execute on the FPGA. Let's start by typing sudo sh. Then we have to source the setup.sh file in the opt xilinx sdx 2017.rte folder. And finally, by typing host and providing the AWS XL bin file, we execute on the FPGA. Awesome! We are currently executing using a cloud-based infrastructure. This is great! What we have seen so far allowed us to request a cloud instance where we have been able to register an image containing the binaries file for our target cloud-based FPGA. The last operation we have to perform is to close our terminal and terminate the instances that we have running. Thanks for watching.